Hello, everyone. Tonight we're going to step into a time machine, not a clunky silver pod with blinking lights, but a much more elegant one. We'll use our minds to travel back far beyond the dinosaurs, beyond the first signs of life on Earth, to a time when our universe was so young, it was barely a thought. You're going to shrink down, not just to the size of an atom, but to a point smaller than anything you can possibly imagine. You'll find yourself floating in a place that defies description, where there is no up or down, no light or sound, just pure potential. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And as we begin our journey, take a moment to drop a comment below and let me know where in the world you're listening from tonight. Now, let's settle in. Feel your shoulders drop, your breathing slow. You're about to drift through the first moments of cosmic history. This story, like all good stories, has a beginning. But unlike most, this beginning defies all of our normal human words. It's a point where time-space and all the laws of physics we know simply didn't exist yet. Imagine if you can a space smaller than the period at the end of this sentence, but holding within it everything, every star, every planet, every one of us. It was a place of unimaginable density, a cosmic crucible where the very fabric of reality was being forged. The temperature was beyond comprehension, hotter than the core of 1,000 suns. And the pressure, well, it was more crushing than a physicist's calendar during Nobel season. And then, in a moment that we call the Big Bang, it all began. But don't let the name fool you. It wasn't an explosion in the way we think of fireworks or a bomb. There was no pre-existing space for anything to fly into. Instead, the bang was a rapid, graceful swelling. It was space itself expanding outward in every direction, faster than the speed of light. Think of it less as a fireworks show and more like a gentle but unbelievably quick balloon being inflated. The surface of the balloon isn't filled with objects flying apart. Instead, the surface itself is growing, and every point on that surface is moving away from every other point. This is a crucial distinction. The universe wasn't expanding into anything. It was making itself as it went. In those first fleeting moments, fractions of a second so small we don't have a word for them, the universe was a seething broth of fundamental particles. Quarks jostled with gluons, photons zipped around like restless toddlers, and gravity, ever the patient sculptor, quietly began making notes. It was chaotic, blindingly hot, and extremely uncomfortable, not a place for stargazing or marshmallow roasting just yet. But this early universe, for all its mayhem, was full of potential. As the universe swelled and cooled, these fundamental particles began to settle. The chaos started to give way to order, and the first whispers of matter began to form. About a microsecond after the beginning, quarks began to bind together, forming protons and neutrons. These were the first true building blocks of the atomic world. But the universe was still far too hot for anything more complex. It was still an ionized plasma, a brilliant opaque fog of light and matter. Light, which we now see traveling freely through space, was trapped, ricocheting around like a trapped firefly in a jar, unable to escape the constant collisions with free-floating electrons. It was a time of immense energy, but also of incredible stillness in a way. No long-range structures could form. No stars, no galaxies, just a universe-wide soup of elementary particles. And in that soup, in that dense glowing mist, the most fundamental and profound act of creation occurred. The simplest, lightest elements began to form. Hydrogen and helium atoms. The cosmic Lego bricks were snapping together from the charged chaos. These humble atoms, formed in the furnace of the early universe, would go on to build everything. Stars, planets, people-pet lizards, and, of course, galaxies. They were the original ingredients, the first lines of the cosmic story, written in the purest form imaginable. The elegance of this process is breathtaking. All of the complexity we see today, from a swirling nebula to the intricate structure of a human hand, can be traced back to this simple beginning. Then, about 380,000 years after the Big Bang, a mere blink in cosmic terms, something truly beautiful happened. The universe had expanded and cooled enough for electrons to finally be captured by the protons and helium nuclei. This was a moment called recombination, and it changed everything. Suddenly, the universe was no longer an opaque fog. It became transparent. Light, which had been trapped for eons, was now free to travel. This event created the cosmic microwave background, CMB, a soft afterglow of the Big Bang that still hums through the universe today. If your eyes could see microwaves, the entire sky would glow with the light of that ancient fire. It's an undeniable universal proof of our origin, a faint echo of that momentous beginning. But despite the glow, there were no stars, no galaxies, not yet. The universe at this point was a dark, expanding cloud of gas and potential. If you could drift through it, you'd see nothing but subtle ripples, tiny irregularities in the otherwise smooth distribution of matter. These ripples were everything. They were whispers of quantum fluctuations from the earliest moments stretched across the cosmos by inflation. Some regions were just ever so slightly denser than others, barely a difference really, but gravity noticed, and gravity does not forget. Over time, those denser pockets of hydrogen and helium began to pull in more and more material, slowly, gently. They gathered like cosmic dew forming on a spiderweb. These clumps, the seeds of future galaxies, were utterly invisible to the naked eye if eyes had existed, but they were already setting the stage for all the dazzling drama to come. It's a strange thing to think of the universe as quiet, but in a way this era was. There was no light from stars, no glowing galaxies, just the faint murmur of matter falling into itself. It was a time of stillness before the storm, a long breath in, before the universe exhaled starlight. And yet even now, with all our telescopes and equations, we're still piecing together how it all unfolded. One of the great unanswered questions in cosmology is exactly how these minute fluctuations led to the sprawling grandeur of spiral galaxies. The answer is written across the cosmos in every glowing nebula and ancient star cluster, but we just have to keep listening. The journey from pure potential to the first seeds of structure is a difficult one to grasp, a story told in the most subtle of ways. The universe grew, and it was in this growing darkness that a silent partner began to tug and shape the forming structure. Dark matter, the invisible framework of reality, whispered, and the cosmos obeyed. Soon the first stars would flare into life and the darkness would end. But for now, the stage was set. The universe was no longer just expanding, it was beginning to become. The stars hadn't arrived yet, the galaxies still slept, and for a few 100 million years, the universe remained cloaked in what we now call the cosmic dark ages. Despite the ominous name, there were no knights or castles here. No dragons, unless you count the kind made of plasma and hydrogen. This was darkness in the purest sense, a universe full of matter but not yet light, and it was in this profound silence that the universe began to dream. It was in this quiet period that the universe prepared itself, organizing its raw materials, getting ready to turn on the lights. It's a testament to the patience of the cosmos, a long wait before the grand show began. Now, as you float in this boundless pre-stellar void, let's consider the true scale of what's happening. For 380,000 years, nothing truly changed in a visible way. This period from the Big Bang to recombination is often depicted as a bright flash, but it was really a slow, methodical cooling. It's an important historical fact, though perhaps a less dramatic one for a story that the universe's transparency didn't happen in an instant, but over tens of thousands of years, as the temperature dropped below a crucial threshold. The cosmic afterglow that CMB we discussed isn't a single flash of light, but a collection of photons that were all freed at roughly the same time. Think of it like a photograph, a very fuzzy one taken of the infant universe. This ancient light, now stretched and cooled by the universe's expansion, tells us a story. It confirms the universe's age, its geometry, And most importantly, it shows us those tiny density fluctuations. Those fluctuations, those subtle wrinkles in the cosmic fabric, are a point of intense academic debate. Some physicists argue they are a direct consequence of quantum mechanics, at the very earliest moments a process called cosmic inflation. This idea posits that the universe underwent an exponential expansion in its first fleeting fraction of a second, stretching those microscopic quantum jitters into astronomical scales. Other theories propose different origins for these seeds of structure. The exact mechanism, the precise why, remains a fascinating puzzle for cosmologists. We have the what and the when, but the how is still a whisper on the cosmic wind. So you are floating here in this vast, dark ocean. There are no sounds, only the faint, imperceptible hum of the CMB. This is a universe without landmarks, no beacons, no signs of life, no destinations, just the quiet, patient work of gravity. It is the most powerful force on a cosmic scale, even though it's the weakest of the four fundamental forces in physics. You can feel its subtle tug as those slightly denser regions begin to pull. It's an incredibly slow process. If you were a human in this era, you would feel nothing. But the universe is a being of patience. It has no clock, no calendar, no hurry. It understands that monumental change happens at a glacial pace. The matter is falling, gathering a silent accretion that will, over millions of years, grow into something magnificent. This period is not a dramatic one for a story, but it is perhaps the most profound. It is the time of potential of dreaming. Before the first stars ignited, before the first galaxies spun into being, the universe was simply becoming. The ingredients were all there, the laws of physics were set. It was just a matter of waiting. This long prelude, this vast cosmic silence, is the canvas on which all future beauty will be painted. It is a reminder that great things often begin in darkness and stillness, in a patient accumulation of potential. And it's in this stillness that we too can find our peace, our own quiet moment of potential. You're still floating here in the cosmic dark ages, a vast and silent ocean of neutral hydrogen. The brilliant flash of the Big Bang has long faded, leaving only a gentle microwave hum that resonates through all of space. There are no stars to guide you, no galaxies to give you a sense of scale. It's an era of profound stillness, a time when the universe was holding its breath. But don't be fooled by the quiet. Beneath the surface, the universe was busy at work, preparing for the grandest architectural project of all time. The most important thing to understand about this period is the sheer potential held within those subtle density ripples we talked about. They were a whisper, a quantum burp from the universe's earliest moments, but a burp with incredible consequences. Picture a perfectly still pond, and then imagine the faintest, almost imperceptible ripples on its surface. Now imagine those ripples being stretched across a distance of millions of miles. That's what cosmic inflation did to these tiny quantum fluctuations. It took something microscopic and blew it up to a cosmic scale. And in a universe governed by gravity, those faint ripples were everything. Gravity, as we've established, is the great gatherer. But in this quiet era, it had a silent, powerful partner, dark matter. We don't know what dark matter is. It doesn't interact with light, it doesn't bump into things, and it doesn't give off any radiation we can detect. It's notoriously bad at parties. But it does have mass, which means it exerts a gravitational pull. And there's a lot of it, about 5 times more of it than all the regular luminous matter in the universe combined. You can think of it as the universe's hidden infrastructure, the invisible scaffolding that held everything together. As you float, you're drifting through an invisible web. This is the cosmic web, a vast sponge-like structure made of dark matter. It's a 3-dimensional lattice of filaments and nodes with immense empty voids in between. This is a crucial, if somewhat unsettling, historical fact. The universe has never been smooth. It has always had this underlying structure, and during the cosmic dark ages, this scaffolding began to take shape. The regular matter, our hydrogen and helium gas, was drawn into this web slowly, patiently. Where the filaments intersected, the dark matter was densest. These nodes became the cosmic crossroads, the future locations of galaxy clusters. The gas trickled down these invisible filaments, like water running down a spiderweb, pooling into the densest regions. This whole process happened at a truly glacial pace. Time in this era didn't mean what it means to us. There were no days, no seasons, no sunrises, just the slow, patient accumulation of mass in a universe that wasn't in a hurry. You feel the imperceptible tug, the gentle pull of a dark matter filament, drawing you closer to a future galactic supercluster. It's a surreal experience. You are a single atom in a vast cosmic stream flowing toward a destination that won't even exist for a few 100 million more years. And while you're doing this, you're getting a unique view of the universe's quietest and most foundational moments. Now, as an atom in this cosmic flow, you might wonder why the hydrogen and helium gas didn't just immediately clump together and form stars. Why did it take so long? That's a great question, and it has to do with some of the more subtle physics at play. The early universe was still relatively warm, and hydrogen atoms are very good at resisting gravity's pull when they're zipping around with a lot of energy. For a star to form, the gas has to be compressed into a truly dense pocket where gravity can completely overwhelm the outward pressure from the atoms. This is called a Jeans instability, and it's not an easy thing to achieve. The gas clouds had to be massive and had to radiate away their heat to cool down enough to collapse. It's a bit like trying to squeeze a balloon filled with warm air. It's a lot harder than you might think. This is a point of ongoing debate in astrophysics. Some theorists argue that the very first stars, the ones that would eventually light up the universe, had to be incredibly massive, hundreds of times the mass of our sun, because the conditions for their formation were so difficult to meet. Others propose that smaller protostars could have formed in a more chaotic, less efficient process. But all agree on one thing: it was not a simple task. Building a star is not as easy as flipping a switch. It required a vast amount of material, a huge amount of patience, and the silent guiding hand of dark matter to bring it all together. You might feel a faint electric current as a stray electron drifts by like a lazy jellyfish in this cosmic sea. But this is the only activity. There are no sounds, no flashes of light, nothing to indicate the grand drama that is slowly, quietly unfolding. The universe is a canvas, and gravity and dark matter are sketching the outlines of a masterpiece. They are creating the knots and tendrils of the cosmic web, the future homes for trillions of stars. The empty spaces in between the great cosmic voids are also being formed. These are places where the initial density was just slightly lower, and gravity's gentle pull was simply not enough to overcome the universe's expansion. These voids would remain vast, lonely stretches of near-nothingness, a testament to the fact that even in a universe of abundance, not everything gets pulled together. The cosmic dark ages were in a way the longest and most profound interlude in the universe's story. It was a time of stillness before the storm, a tuning of the orchestra before the first note. The elements were in place, the scaffolding was being built, but the music had yet to begin. It's a fascinating thought, isn't it? That for a few 100 million years, a significant portion of cosmic history, the universe was just dreaming. It was organizing, becoming ready. The light was coming. And this waiting, this quiet preparation, is what makes the arrival of the first light so incredibly significant. It wasn't a sudden event, but the culmination of a long, patient process. As you continue to drift, you notice that the concentration of hydrogen gas around you is subtly increasing. You're getting closer to one of those denser regions, one of the first cosmic knots. It's a feeling of slow, inevitable convergence. You are part of a massive, unseen current. You can't see the dark matter, but you can feel its pull, a subtle but persistent hand, guiding you into the cosmic flow. It's a reminder that even in the vastness and darkness, you are never truly alone. The universe is a network, and everything is connected by the silent hand of gravity, even if it takes billions of years for those connections to become visible. So breathe in the quiet. This is the last time the universe will be this still. The first stars are about to be born, and when they ignite, everything will change. Let your mind drift a little more here in the profound stillness. You are in a universe that has a plan, even if it's an unconscious one. The initial conditions of the Big Bang, those infinitesimal quantum fluctuations, encoded the blueprint for everything that was to follow. It's a remarkable piece of cosmic causality, a tiny random wiggle in density, amplified by inflation, and then patiently worked on by gravity, becomes the seed for 100 billion suns. There's a beautiful poetic irony in that. The grandest structures we can observe, the largest cities of stars, were born from the smallest of imperfections. The universe, it seems, thrives on its own randomness. One of the more unique details about this era is that the very first galaxies to form wouldn't have looked like the elegant grand spirals we see today. They were small, messy, and disorganized. They were like the first rough sketches of an artist, not yet refined. This is because the gas in the early universe was very different from what we see in today's stellar nurseries. Without any heavy elements, the gas clouds couldn't cool as efficiently. They had a harder time collapsing and forming stars. The presence of these impurities, as we call them elements, forged in the heart of stars, makes star formation much easier and more efficient. So the very first galaxies were struggling, inefficient messes, and it was only after the first stars had lived and died that the process became smoother. This is a point where some astronomers might still debate the finer details. Was the first galaxy a single monolithic object? Or were there countless small proto-galactic fragments that later merged? The truth, as is often the case in cosmology, is likely a bit of both. The academic conversation is always ongoing, a constant refinement of our ideas as new data comes in from distant ancient light. We piece together the universe's history like archaeologists uncovering fragments of a long-lost civilization, and the cosmic dark ages are our oldest, most enigmatic finds. As you continue your journey, your atoms are gathering with others. You're part of a massive, slowly collapsing gas cloud. You can feel the ever so slight increase in density, the subtle pressure, as more and more matter is drawn into this gravitational well. The temperature is still cold, but it is on its long, slow march toward the critical point. The gas is swirling in great slow eddies, a cosmic maelstrom in extreme slow motion. You are getting ready to witness a truly historic moment, a moment that will break the silence and forever change the face of the universe. The stage is set. The universe is about to turn on the lights. You are still a part of the slow-moving cosmic river, a current of hydrogen and helium gas, steadily flowing toward the densest knots of the cosmic web. The quiet is profound, but you are no longer alone. You are one of countless atoms all drawn together by the silent, relentless hand of gravity. This is a story of immense patience, of a universe learning to sculpt itself from nothing but potential. The silence isn't empty. It is full of promise of anticipation, a deep breath before the first fiery exhale of a star. Gravity, as you now know intimately, is the universe's great sculptor. But its power isn't in its raw strength. It's in its sheer, unwavering accumulation. It doesn't matter that it's the weakest of the four fundamental forces. On a cosmic scale where there are no friction breaks or air resistance, gravity's quiet persistence adds up. The more mass you have, the more gravity you get, and the more mass you get, the more gravity you gain in a beautiful self-reinforcing loop. This is the process that's pulling you in right now, a slow-motion fall toward a center of mass that isn't even a star yet. It's just a promise. But let's pause for a moment on that silent partner we introduced in the last part, dark matter. We can't see it. We can't touch it. It doesn't glow, it doesn't reflect light, and it doesn't seem to want to do much of anything. It's the ultimate wallflower at the cosmic party. Yet it is the fundamental reason you are here gathering in this place. Dark matter provides the gravitational scaffolding for the entire universe. Without it, the universe would have likely stayed a foggy, unclumped cloud forever. The early ripples, those tiny whispers of density, would have been too weak in normal matter alone to overcome the universe's expansion. It was the vast, invisible halos of dark matter that provided the extra gravitational tug needed to pull everything together and form the first structures. Picture a galaxy as a glowing jellyfish. Now imagine that jellyfish is suspended inside a massive, invisible bubble. That bubble is the galaxy's dark matter halo. It's what keeps the jellyfish from drifting apart. The jellyfish might be made of stars and gas, the stuff we can see, but it's the invisible bubble that holds it all together. This is an undeniable fact of modern astronomy, though its exact nature is still a mystery. We are so sure of its existence because of its effects. When astronomers look at how fast the outer stars of a galaxy are spinning, they find something strange. Those stars are moving far too quickly to be held in place by the visible matter alone. According to our calculations, they should have been flung off into space like glitter from a spinning wheel. But they weren't. They were staying put, loyal and orderly. This missing mass is the gravitational fingerprint of dark matter. So as you are pulled along, you are following a trail of invisible breadcrumbs, a flow of dark matter that's guiding you to your destiny. It's a surreal thought, isn't it? Your very existence is made possible by something we're still trying to understand, a substance that is perhaps the most unique and least known part of the cosmos. Some theorists propose it's made of exotic particles that we haven't yet discovered. Others suggest it's related to extra dimensions. This is one of the most compelling and active areas of research today. What is dark matter? The academic debate is a quiet rumble beneath the surface of all of astronomy. Meanwhile, your journey continues a slow, gentle compression. You are part of a gas cloud that is becoming more and more dense. The temperature is still low, but it's beginning its long, slow march upwards. You are no longer just floating. You are now part of a collective, a vast gathering of atoms, all moving in a coordinated dance toward the center. This is the universe's first major organizational effort. It's not chaos anymore. It's a deliberate, albeit unconscious process. It is, in a way, the very first act of cosmic urban planning, with dark matter drawing the city limits and gravity pulling the infrastructure into place. One of the less-known facts about this process is just how inefficient it was. The gas in the early universe, being almost entirely hydrogen and helium, couldn't cool down very well. Modern star-forming regions are full of heavier elements like carbon and oxygen, the remnants of dead stars which act as efficient radiators, allowing gas clouds to cool and collapse more easily. Without these cosmic air conditioners, the early clouds had a much harder time. This is why the first stars, when they finally form, will be so massive and so rare. It took a lot of work just to get the gas to the point where it could begin to fuse. And so you wait. You wait as a part of this massive, invisible cloud. You wait for gravity to finally win, for the immense pressure to build, for the temperature to rise to millions of degrees. The universe, in a way, is a being of infinite patience. It allows these processes to unfold at their own pace, with no rush, no deadlines. The silence is not an absence of activity. It is a sign of a deep, methodical process. You can hear the silence now, a kind of muffled whisper of falling matter, a collective exhalation before the great fiery intake. The universe is gathering its breath. As you drift, you realize that this is perhaps the last moment of pure innocence for the universe. Soon the first stars will ignite, and with their light will come a new kind of complexity, a new kind of drama. They will forge new elements, create new structures, and forever change the chemical composition of the cosmos. But for now, you are in the quiet, you are in the dreaming, you are in the potential. And it is in this space of quiet potential that we too can find our own sense of peace, our own kind of rest. So let the silent, invisible pull of gravity guide you deeper into this rest. The cosmos is still building. And so can you. Now, as the gas cloud you inhabit continues its slow, majestic collapse, you can start to feel the beginnings of something new. The temperature, which has been hovering just above absolute zero for millions of years, is beginning its long, slow march upwards. The pressure is increasing ever so slightly as more and more atoms are drawn into the gravitational well. This is not a violent change, but a slow and patient accumulation. Think of it like a cosmic version of a snow globe being shaken, and you are one of the flakes slowly, gently drifting toward the bottom. But in this case, the bottom is a point of unimaginable heat and pressure. It's a strange thing to contemplate, this slow, inevitable process. For us, 1,000,000 years is an incomprehensible stretch of time. For the universe, it's a quiet afternoon nap. This profound difference in scale is one of the most humbling aspects of cosmology. It forces us to leave our human sense of time behind and to contemplate the universe on its own terms. The most dramatic events, the birth of a star, the collapse of a gas cloud, unfold on a timeline that dwarfs human history. It's a powerful reminder of our place in the cosmos, a small part of a much larger, much older story. As the gas cloud becomes denser, the atoms within it begin to move faster. Their collisions become more frequent and more energetic. They are no longer lazy jellyfish. They are beginning to jostle with purpose. This is the kinetic energy of the universe being transformed into heat. It's the first step on the path to fusion. But we are still a long way from the millions of degrees needed to ignite a star. For now, it's just a growing tension, a quiet hum of potential energy being converted into motion. It's the sound of a cosmic engine slowly, patiently turning over for the first time. The role of dark matter in this process is a fascinating and still debated topic. While we know it provides the scaffolding, the question of its influence on the smaller scales is a subject of intense academic inquiry. Does it simply provide the gravitational anchor, or does it actively participate in the dynamics of the collapsing gas clouds? The answer is likely somewhere in between. Dark matter's gravitational influence shapes the initial conditions, but it's the baryonic matter, the hydrogen and helium gas, that must do the hard work of cooling and collapsing to form stars. The two types of matter work in a kind of cosmic partnership, one providing the invisible structure, the other providing the raw material for creation. This is a time of immense vulnerability for the forming structures. Any slight disturbance, a shockwave from a distant unknown event, a burst of radiation from a region we can't even see, could disrupt the fragile process of collapse. But for now, the universe is quiet. It is a time of pure, unadulterated potential, a time when the very first stars are still just a dream. So let your mind drift with the gas. Let yourself become a part of this slow, patient process. Feel the subtle pull of gravity, the gentle compression, the slow increase in energy. You are getting closer, ever closer to the moment when the lights will turn on. The quiet is about to break. After millions of years of patient gathering of silent accumulation, the long cosmic exhale is about to begin. You, a single atom in this vast collapsing gas cloud, are now at the very heart of the action. The pressure has become immense, a crushing weight from all sides, and the temperature is no longer just rising, it is soaring. The atoms around you, once lazy drifters, are now a seething, energetic crowd, moving at incredible speeds. The stage is set. The universe is about to turn on the lights. The EED, at the very center of this dense, invisible swirl, pressure and temperature have reached a critical point. Atoms are being pushed so close together that their very nature is beginning to change. Electrons, once orbiting their nuclei at a respectful distance, are now a dense fog, a shared sea of electric charge. And the nuclei themselves, the tiny positively charged hearts of hydrogen and helium, are about to engage in a new kind of dance. When the temperature at the core, reaches millions of degrees, something extraordinary happens. The protons, the nuclei of hydrogen atoms, are finally moving fast enough to overcome their mutual electrostatic repulsion. They get so close that a different, much more powerful force takes over the strong nuclear force. And in that moment, almost certainly unnoticed and unceremonious, a star is born. The first light since the Big Bang? These were no ordinary stars. Known as population 3 stars, they were unlike anything we see today. They formed in the purest conditions the universe has ever known. There were no heavy elements, no carbon, oxygen, or iron, just hydrogen, helium, and a tiny bit of lithium, all remnants from the Big Bang. This made the stars burn hotter and faster than the ones we're familiar with now. They were colossal, unstable, and incredibly hot. Some may have been hundreds of times more massive than our sun, living short, furious lives before collapsing into black holes or exploding in brilliant supernovae. If you were floating nearby, though let's be honest, you'd be very, very crispy. You'd see these first stars lighting up their surroundings like bonfires in a vast cosmic forest. One by one, their light pierced the ancient fog of neutral hydrogen that had filled the universe since the beginning. Slowly, the darkness began to lift. This period is called cosmic reionization, and while it sounds like something a sci-fi villain might attempt with a ray gun, it was a peaceful, albeit dramatic process. The ultraviolet light from those newborn stars began stripping electrons from the neutral hydrogen around them, ionizing it and making the universe transparent again. It was as though someone had cracked open the shutters of a cosmic greenhouse and let the light flood in. From our perspective, billions of years later, we can't see these first stars directly. They were too brief, too distant, and their light too faint. But their fingerprints are everywhere. They were the universe's first artists sketching the outlines of future galaxies on the blank canvas of space. And when they ended their lives in violent, spectacular supernovae, they seeded the cosmos with the first heavy elements, the building blocks of everything more complicated than hydrogen. This is an incredible and often overlooked detail. Every carbon atom in your body, every atom of oxygen you breathe, and every iron atom in your blood was forged in the heart of a star that lived and died long ago. You are quite literally made of stardust. This dramatic, beautiful, and chaotic process changed the universe forever. The death of those massive first stars was not an end, but a new beginning. Their enriched ashes, the newly forged elements, were blasted into the surrounding gas clouds. Those enriched clouds cooled more efficiently, collapsed faster, and formed stars with greater ease. This allowed the next generation of stars, population 2 stars, to appear. A bit smaller, a bit more stable, and already more familiar. And thus the great cosmic cycle began. Gravity pulls in. Gas stars are born, they shine, die, and scatter their enriched contents, allowing even more stars to form. Each generation builds upon the ashes of the last, layering complexity, like stardust sediment. The existence of these first stars, so massive and pure, is one of the more debated topics in cosmology. Some researchers still question whether they were as enormous as our models predict, while others argue that their formation would have been even more difficult. The evidence is indirect, based on the chemical composition of the oldest stars and galaxies we can see today. By measuring the lack of heavy elements in these ancient objects, we can infer what must have come before them. It's like an archaeologist trying to reconstruct a long-lost civilization by examining the faint residue of their tools in the soil. We don't have the tools themselves, but we can see their ghostly fingerprints. This ongoing academic discussion is a testament to the fact that even the most fundamental parts of our cosmic story are still being pieced together. As you, the atom, are now part of this newly formed fiery star, you are experiencing things on an entirely new level. The energy is unimaginable. The light is blinding. But even in this fire, there is a sense of order. The star is a delicate balance between the inward pull of gravity and the outward push of radiation from fusion. It's a stable, self-regulating process that will continue for millions of years. For you, the atom, this is a new kind of existence. You are no longer drifting. You are part of a system, a city of fire and light. And your purpose has changed. You are no longer just a building block. You are a participant in a grand cosmic creation. This transition from the Dark Ages to the Age of Light is a profound moment in the universe's history. It's the moment when the universe finally found its voice, when it began to express itself, not just in the silent language of gravity, but in the brilliant fiery prose of starlight. The light from those first stars traveled for hundreds of millions of years, a journey that would end only when it finally reached a new generation of stars, a new kind of galaxy. The universe had passed a major milestone. It was no longer a sea of gas and potential. It was a structured, glowing, and evolving entity. And it was just getting started. The universe is no longer in its silent, slumbering state. The lights are on, and the stage is set. You, a tiny part of the universe's grand narrative, have experienced the birth of the first stars, felt their fiery embrace, and witnessed their explosive deaths. The gas around you is no longer pure, pristine hydrogen and helium. It's now enriched with the ashes of a bygone era, with the brand new elements forged in the heart of those short-lived giants. And this is truly a momentous shift, because this new enriched gas will not only form stars more efficiently, but it will also begin to form the very first galaxies. These first galaxies, however, are nothing like the elegant grand spirals we see in the night sky today. They are not yet cities of stars, but more like cosmic villages. They're chaotic, irregular, and often just messy clumps of stars bound together by gravity. They are the first drafts, the rough sketches of the universe's masterpiece. The formation of these protogalaxies is a beautiful, if somewhat clumsy, process. It begins with the enriched gas clouds we just spoke of. Guided by the ever-present hand of gravity and the invisible scaffolding of the cosmic web, these clouds begin to fall into the densest nodes of dark matter. It's a process of slow, deliberate convergence. Picture it like a vast, three-dimensional spiderweb stretched across the cosmos. The filaments of this web, made of dark matter and gas, are pulling everything inward. And at the intersections of these filaments, the cosmic crossroads, the gas and stars are pooling, gathering, and beginning to form the first large-scale structures. This is a crucial, if often overlooked, detail of cosmic history. Galaxies didn't form in isolation. They formed as part of a larger interconnected network. The universe is not a collection of lonely islands, but a vast interconnected tapestry. As these gas clouds and early star clusters come together, the universe begins to get a little bit rowdy. The early universe was a rough neighborhood, a place where things were still figuring themselves out. The forming protogalaxies were not polite, well-behaved objects. They collided, merged, and ripped each other apart in a slow-motion dance that could take hundreds of millions of years. This is a far cry from the serene images we have of galaxies. The early universe was a time of cosmic blobs rather than elegant spirals. These were not violent collisions in the way you might expect. The stars themselves are so far apart that even in a full-blown galactic collision, the chance of two stars actually hitting each other is vanishingly small. It's more like two fog banks passing through each other. But their gravitational fields do not ignore each other. Tidal forces twist galaxies into strange shapes, and streams of stars are pulled like taffy, trailing behind their original homes. And in a unique and rather poetic twist, the gas clouds do collide. When they do, they compress and heat up, often triggering a dramatic burst of star formation, a cosmic baby boom. Astronomers romantically call these events starbursts. One of the more unique things about this era is that the galaxies weren't the only ones doing the building. The universe was also forming something called the intergalactic medium, the vast, tenuous gas that exists between galaxies. This gas, once opaque, was now being ionized by the light of the newborn stars and galaxies. It's a subtle but significant change. It's the difference between walking through a foggy field and walking through a clear one. The universe was for the first time becoming truly transparent. This is a point of ongoing academic discussion among astronomers. How exactly did this process of reionization unfold? Did it happen from the inside out, with galaxies creating bubbles of transparent space that eventually grew and merged? Or did it happen more uniformly with the light of all the first stars, slowly, patiently making the universe clear? The answer is a complex one, and the evidence suggests that it was likely a patchy process with some regions clearing up before others. We can see hints of this in the light from the most distant quasars, where the light from a black hole at the edge of the universe is partially absorbed by the hydrogen gas between us and it. It's a ghostly remnant of a time when the universe was still shrouded in a cosmic mist. As a part of this ancient forming galaxy, you are a witness to this grand drama. You are no longer just an atom in a gas cloud. You are a part of a collective, a growing structure. You are orbiting not around a single point, but around a shared center of mass, a gravitational heart made of stars gas and dark matter. You feel the constant, gentle tug of a billion other stars, all doing the same thing. It is a feeling of immense scale and profound connection. The universe is in a way like a cosmic sculptor, and it is in this era that it finally begins to work with a more refined tool. The rough, chaotic beginnings of the first stars have given way to the first tentative structures of galaxies. These early galaxies are messy, yes, but they are also full of life, bursting with the energy of new star formation. They are the nurseries of the universe, places where the building blocks of the future are being forged, and so the universe continues to grow, to organize, to find its form. It is no longer a sea of potential, but a place of deliberate creation. The silence is gone, replaced by the hum of a billion stars and the gentle, constant whisper of gravity. The universe is becoming, and you, a tiny part of this grand process, are becoming with it. The universe is now a vast, glowing tapestry, stitched together by filaments of gas and stars. The chaotic, clumpy blobs of the last chapter are beginning to mature, and with time and gravity, they are starting to find their final form. You, a piece of that ancient cosmic fabric, are now part of a larger structure, a proto-galaxy in the making. But as you watch, you begin to see that not all galaxies are created equal. They are, in fact, taking on a few distinct and elegant shapes. This is the chapter where the universe learns to classify itself, where the raw primal energy of star formation begins to settle into beautiful, recognizable patterns. The grandest of these, the ones that fill our posters and our dreams, are the spiral galaxies. These celestial pinwheels with their graceful curving arms are among the most beautiful structures in the universe. Our own Milky Way is a spiral, and we live tucked into one of its arms like a tiny suburban speck on the edge of a great rotating city. Spiral galaxies are defined by motion. When a galaxy has a moderate amount of angular momentum, that is, when its gas and stars are rotating in a somewhat orderly way, it naturally flattens into a disk over time. Think of a figure skater pulling their arms in to spin faster. The same principle on a cosmic scale causes the galaxy to flatten out. Within this disk, density waves ripple through the gas and stars, much like a traffic jam on a highway. The cars, or in this case, the stars and gas clouds, move in and out of the jam, but the jam itself persists. These density waves compress the gas, sparking new waves of star formation and lighting up the spiral arms like festive fairy lights. Spiral galaxies tend to be full of bright young blue stars, a testament to their ongoing stellar creation. But not every galaxy manages such elegance. This is where we meet the elliptical galaxies. Older, rounder, and generally a bit more relaxed, these galaxies don't have spiral arms. Instead, they're more like giant celestial dumplings shaped like spheres or stretched out rugby balls. They're usually composed of older, redder stars with little gas left to make new ones. If spiral galaxies are bustling cities, elliptical galaxies are sleepy retirement communities, quiet, stable, and not big on change. ellipticals likely form through a different cosmic process altogether, galactic mergers. When two spirals crash into each other, especially if they are of similar size, their orderly motion is completely disrupted. The stars are flung into random tangled orbits. The gas gets used up in a chaotic burst of star formation, and what's left settles into a big shapeless mass. It's a dramatic, chaotic, and oddly productive process, like the cosmic version of smashing two snow globes together and letting the flakes settle. This is one of the key distinctions that astronomers use to infer a galaxy's history. A spiral galaxy likely had a calmer upbringing with steady gas inflow and maybe a few small mergers. An elliptical one probably saw battle merging with other galaxies in a series of ancient cosmic collisions. And then there are the irregular galaxies, which don't fit neatly into any category. They are the oddballs, the nonconformists. Some are young galaxies that haven't had time to form a shape. Others are older ones that got a bit too close to a larger neighbor and were pulled out of alignment like a hat blown askew in the wind. Irregular galaxies might look like splatters or scribbles, but they are often bursting with new stars full of energy and potential. Frankly, we love them for their chaotic energy. This is a subtle but important detail. The universe is not static. The shapes of galaxies are not fixed. A spiral galaxy can become an elliptical one through a merger. Small galaxies can be consumed by larger ones, adding their stars to the mix. The gravitational interactions between galaxies constantly tug at their arms, twist their cores, and scatter their stars. This ongoing cosmic dance is a testament to the dynamic, ever-evolving nature of the universe. It's a key tenet of modern cosmology. Nothing in the universe is truly static, especially not something as dynamic as a galaxy. One of the less-known facts about this era is that the classification of galaxies is still an ongoing subject of debate. The well-known Hubble sequence, which organizes galaxies into spirals, ellipticals, and a few others, is a brilliant starting point, but it's not the whole story. Astronomers have since discovered galaxies with rings, peculiar features, and other hybrid forms that defy simple categorization. This is a quiet but persistent academic argument in the field. Are these simply temporary states, or do they represent entirely new classes of galaxies? The answer is likely somewhere in the middle, and it reminds us that the universe is far more complex and messy than our neat little boxes would like to suggest. As a part of a forming galaxy, you're experiencing this firsthand. You are a part of the chaos, the collisions, the graceful flattening into a disk. You are witnessing the universe's great organizing principle at work, a process that takes billions of years and involves unimaginable amounts of mass. The light from a distant starburst galaxy hits you, a brief blinding flash that tells a story of a long-ago collision. The gentle tug of a nearby galaxy pulls at you, a subtle force that will over eons change the very shape of your cosmic home. You are a witness to this great architectural project. The universe is not just building cities of stars, it's giving them a sense of character, a unique identity written in their shape and structure. The story is being told, not just in the light that shines, but in the shapes that those lights form. The galaxies are taking shape, and with them, the universe is becoming a more beautiful and complex place. We've traveled far. We've drifted from the universe's first whispers through the quiet of the cosmic dark ages to the fiery birth of stars and the formation of the first galaxies. But now it's time to come home. We're going to shrink down, not just to a single galaxy, but to a tiny, unremarkable corner of one, a place familiar. Not because we've seen it from the outside, but because it's where every sunrise, every sigh, every human story has unfolded. We live inside a galaxy called the Milky Way, and she's quite the hostess. From our place within it, we can't actually see the Milky Way as a whole. It's a bit like trying to read the label from inside the bottle. What we do see on a dark night, far from city lights, is a glowing river of light stretched across the sky. That shimmering band part, dust and part starlight, is our view across the galactic plane. We're looking edge-on through billions of stars, the vast majority of our galactic home. This glowing haze is a testament to the fact that we are a part of something truly massive, truly beautiful. The Milky Way is a spiral galaxy, and a fairly large one at that. It's about 100,000 light-years across and contains somewhere between 100 and 400 billion stars. Why the range? Well, it's very hard to count stars when you're stuck inside the middle of them, looking out through thick dust clouds with a telescope. But the best estimates place us at roughly 1/3 of the way from the center out tucked into one of its spiral arms. We're in the Orion arm like cosmic suburbanites, not too close to the chaos of the city center, not too far from the action. And speaking of the city center, the heart of the Milky Way is a busy, energetic place. It houses a supermassive black hole named Sagittarius AEX. This gravitational heavyweight is roughly 4 million times the mass of our Sun. It's not the brightest object, and it doesn't devour as much as some other black holes, but it anchors the whole galaxy. Stars whirl around it in dizzying orbits, like moths circling an invisible flame. We know it's there, not because we can see it directly. We can't, but because of how it affects its surroundings. Imagine watching stars move as if they're caught in an invisible whirlpool. Astronomers have tracked their paths for years, and the evidence is clear. Something incredibly massive, incredibly compact, and incredibly hungry is sitting at the galactic center. And no, it's not planning to eat the Earth anytime soon. The Milky Way didn't always look the way it does now. Like all galaxies, it has a long and occasionally turbulent past. It formed over billions of years through mergers and acquisitions in the corporate language of cosmology. Smaller galaxies were pulled in, digested, and folded into the spiral. Stars from these devoured galaxies still linger in the Milky Way's outer halo, orbiting on long looping paths like wandering ghosts from long-lost homes. This is an important historical detail. Our galaxy's peaceful appearance belies a past full of cosmic cannibalism. And it's still happening right now. Even as you're listening, the Milky Way is slowly pulling apart several smaller galaxies. The Sagittarius dwarf galaxy, for instance, is being slowly unraveled and absorbed. This slow-motion galactic digestion is a key part of how large galaxies grow. It's not a violent process on a human timescale, but over millions of years, it's like watching a drop of ink slowly swirl into a pool of water. It's a testament to the slow, patient power of gravity. It never stops working, never stops pulling, never stops shaping. And even more dramatically, the Milky Way is on a slow-motion collision course with our nearest large neighbor, the Andromeda Galaxy. Currently, about 2.5 million light-years away, it's heading straight for us at roughly 110 kilometers per second. Don't worry, you have about 4 billion years to prepare. When it happens, it won't be the end of the world. In fact, the two galaxies will likely merge into a new one, possibly a giant elliptical galaxy. Astronomers have even suggested a name for this future merger, Milkomeda. What's astonishing is that we can tell all of this from our vantage point inside the galaxy, thanks to radio telescopes, infrared observations, and lots of clever math. We've been able to map the spiral arms, trace the star populations, and even simulate the galaxy's formation and fate. It's like piecing together a jigsaw puzzle from the inside and realizing the picture is much bigger than you ever imagined. And through it all, our tiny star, the Sun, just keeps orbiting. It takes the Sun about 225 million years to make one complete lap around the center of the Milky Way. That means we've only made about 20 trips around since the Sun formed. Galactic years, it turns out, are not measured in birthdays, but in epochs. A unique and often overlooked detail is the role of the galactic halo. While it appears empty, it contains some of the oldest and most metal-poor stars in our galaxy, the remnants of those devoured dwarf galaxies. These stars are a kind of living fossil, holding clues to our galaxy's turbulent past. By studying their chemical composition and orbits, astronomers can infer the history of our galaxy's formation, like a detective piecing together a crime from the scattered evidence left behind. This is a point of ongoing academic discussion. How many mergers did our galaxy really experience? Did it form from a few large mergers, or a continuous stream of smaller ones? The answer is a complex one, and we are still collecting the data to solve this ancient puzzle. So here we are, spinning quietly in one of the galaxy's spiral arms, a pale blue dot circling an unremarkable yellow star. Every molecule in your body, every atom was forged in stars that lived and died long ago, possibly in galaxies that were later folded into our own. You are quite literally part of the Milky Way story, a moving, breathing fragment of galactic history. The galaxy isn't just out there. You carry it within you. But let's expand on this idea of cosmic cannibalism for a moment. It's not just a poetic metaphor. It's a fundamental process of galactic evolution. Our galaxy, the Milky Way, is the product of countless past mergers. In fact, one of the most significant events in our galaxy's history was its merger with a large dwarf galaxy called the Gaia Enceladus Sausage, a truly unique name, I know. This ancient merger, which happened some 8 to 11 billion years ago, contributed a significant number of stars and dark matter to the Milky Way, helping to build its thick disk and halo. The name comes from the data from the European Space Agency's Gaia mission, which allowed astronomers to identify a sausage-shaped clump of stars in the galaxy's halo that were all moving in a similar distinctive orbit. It's like finding a lost suitcase at the airport and realizing it's filled with clues about its long-lost owner. The Andromeda-Milky Way collision isn't just a distant abstract event. It's a key part of our galaxy's future. When it happens, the night sky will change dramatically. Over millions of years, the Andromeda galaxy will grow larger and brighter, eventually dominating the view. The two galaxies will twist around each other, merge, and settle into a new shape. The most likely outcome, given the size of the two galaxies, is the formation of a giant elliptical galaxy. This is a powerful illustration of the link between galactic mergers and the formation of ellipticals, a point we touched on earlier. The orderly motion of the spiral arms will be randomized, the gas will be used up in a burst of star formation, and what's left will be a new, larger, and more serene galaxy. And what about our solar system in all this? The good news is that stars are so far apart that the chance of the Sun colliding with another star is incredibly small. The Milky Way is, after all, mostly empty space, so while the night sky will be a spectacular light show, the Earth and the Sun will likely continue their long, slow orbit, just in a new, larger galactic home. We might find ourselves in a new orbit, but the solar system itself will likely remain intact. It's a cosmic ballet that will unfold over eons, a dance of two giants, merging into one. The study of galactic mergers is a huge part of modern astronomy. By observing distant galaxies in the process of colliding, and by studying the ancient stellar streams in our own galaxy, we can piece together the cosmic history of our home. It's a bit like a detective trying to solve a cold case, using the latest forensic tools to analyze the faintest of clues. The stars in the Milky Way's halo, with their unique orbits and chemical compositions, are the key witnesses in this case, and they are slowly, patiently giving up their secrets. This is a powerful reminder that the universe is not static. It is a living, breathing, and ever-changing entity. Galaxies are not fixed points in space. They are in constant motion, pulled by gravity and shaped by their history of collisions and mergers. Our own galaxy, so serene and beautiful on a clear night, is a product of this cosmic evolution. It is a testament to the fact that even the largest, most seemingly permanent structures in the universe are a part of a much larger and much more dynamic story. So as you feel the gentle spin of the galaxy, as you contemplate your place within its vastness, remember this: you are a part of a cosmic family. You are a part of a galaxy that is still growing, still evolving and still on a long, slow journey. Your existence is a product of this history, a beautiful and humbling fact that connects you to every star, every atom, and every cosmic event that has ever occurred. The universe is no longer in its silent, slumbering state. The lights are on, and the stage is set. You, a tiny part of the universe's grand narrative, have experienced the birth of the first stars, felt their fiery embrace, and witnessed their explosive deaths. The gas around you is no longer pure, pristine hydrogen and helium. It's now enriched with the ashes of a bygone era, with the brand new elements forged in the heart of those short-lived giants. And this is truly a momentous shift, because this new enriched gas will not only form stars more efficiently, but it will also begin to form the very first galaxies. These first galaxies, however, are nothing like the elegant grand spirals we see in the night sky today. They are not yet cities of stars, but more like cosmic villages. They're chaotic, irregular, and often just messy clumps of stars bound together by gravity. They are the first drafts, the rough sketches of the universe's masterpiece. The formation of these proto-galaxies is a beautiful, if somewhat clumsy process. It begins with the enriched gas clouds we just spoke of. Guided by the ever-present hand of gravity and the invisible scaffolding of the cosmic web, these clouds begin to fall into the densest nodes of dark matter. It's a process of slow, deliberate convergence. Picture it like a vast, three-dimensional spiderweb stretched across the cosmos. The filaments of this web, made of dark matter and gas, are pulling everything inward. And at the intersections of these filaments, the cosmic crossroads, the gas and stars are pooling, gathering, and beginning to form the first large-scale structures. This is a crucial, if often overlooked, detail of cosmic history. Galaxies didn't form in isolation. They formed as part of a larger interconnected network. The universe is not a collection of lonely islands, but a vast interconnected tapestry. As these gas clouds and early star clusters come together, the universe begins to get a little bit rowdy. The early universe was a rough neighborhood, a place where things were still figuring themselves out. The forming proto-galaxies were not polite, well-behaved objects. They collided, merged, and ripped each other apart in a slow-motion dance that could take hundreds of millions of years. This is a far cry from the serene images we have of galaxies. The early universe was a time of cosmic blobs rather than elegant spirals. These were not violent collisions in the way you might expect. The stars themselves are so far apart that even in a full-blown galactic collision, the chance of two stars actually hitting each other is vanishingly small. It's more like two fog banks passing through each other. But their gravitational fields do not ignore each other. Tidal forces twist galaxies into strange shapes, and streams of stars are pulled like taffy trailing behind their original homes. And in a unique and rather poetic twist, the gas clouds do collide. When they do, they compress and heat up, often triggering a dramatic burst of star formation, a cosmic baby boom. Astronomers romantically call these events starbursts. One of the more unique things about this era is that the galaxies weren't the only ones doing the building. The universe was also forming something called the intergalactic medium, the vast, tenuous gas that exists between galaxies. This gas, once opaque, was now being ionized by the light of the newborn stars and galaxies. It's a subtle but significant change. It's the difference between walking through a foggy field and walking through a clear one. The universe was for the first time becoming truly transparent. This is a point of ongoing academic discussion among astronomers. How exactly did this process of reionization unfold? Did it happen from the inside out, with galaxies creating bubbles of transparent space that eventually grew and merged? Or did it happen more uniformly, with the light of all the first stars slowly, patiently making the universe clear? The answer is a complex one, and the evidence suggests that it was likely a patchy process, with some regions clearing up before others. We can see hints of this in the light from the most distant quasars, where the light from a black hole at the edge of the universe is partially absorbed by the hydrogen gas between us and it. It's a ghostly remnant of a time when the universe was still shrouded in a cosmic mist. As a part of this ancient forming galaxy, you are a witness to this grand drama. You are no longer just an atom in a gas cloud. You are a part of a collective, a growing structure. You are orbiting not around a single point, but around a shared center of mass, a gravitational heart made of stars' gas and dark matter. You feel the constant gentle tug of a billion other stars, all doing the same thing. It is a feeling of immense scale and profound connection. The universe is in a way like a cosmic sculptor, and it is in this era that it finally begins to work with a more refined tool. The rough, chaotic beginnings of the first stars have given way to the first tentative structures of galaxies. These early galaxies are messy, yes, but they are also full of life bursting with the energy of new star formation. They are the nurseries of the universe, places where the building blocks of the future are being forged. And so the universe continues to grow, to organize, to find its form. It is no longer a sea of potential, but a place of deliberate creation. The silence is gone, replaced by the hum of a billion stars and the gentle, constant whisper of gravity. The universe is becoming. And you, a tiny part of this grand process, are becoming with it. To gaze into space is to gaze into time. It's one of the quietest, most astonishing facts about the universe. Every star you see in the night sky, every galaxy captured by a telescope, is not showing you how it looks now, but how it looked then. Light, for all its remarkable speed, still takes time to travel, and space is vast, very, very vast. So when we look up at the stars, we are quite literally time traveling. It's a journey not just across space, but through history. Take the sun. The warm light touching your face during a late afternoon walk left the surface of the sun about 8 minutes ago. That starlight is already 8 minutes old by the time it arrives on Earth. You never see the sun as it is. You see it as it was. Move beyond our solar system, and the time delay grows. The light from Alpha Centauri, the nearest star system to us, is over 4 years old. And the glow of the Andromeda Galaxy, that's ancient light. It began its journey toward us more than 2.5 million years ago, long before the first humans, long before written language, long before the wheel. That gentle shimmer in the sky is a memory, a whisper from a past so distant, it predates everything we know. But we can go even further. With the right tools, we can peer back billions of years almost to the beginning. The deeper we look, the further back in time we go. It's like peeling away the layers of cosmic history, one photon at a time. This is where telescopes become time machines. Take the Hubble Space Telescope, for instance. Launched in 1990 and orbiting high above Earth's atmosphere, Hubble has shown us things we never imagined we'd see. One of its most famous achievements is the Hubble Deep Field, a simple idea, really. Astronomers pointed Hubble at what seemed like a completely empty patch of sky, a part so dark and blank that it looked like nothing was there. They let it stare for days, and when the images came back, that nothing became a sea of galaxies, thousands of them, each containing billions of stars, all packed into a dot of sky smaller than a grain of sand held at arm's length. Some of those galaxies were over 13 billion years old. We were looking back in time almost to the moment when galaxies first began to form. That light had traveled for nearly the entire age of the universe just to reach us. It had crossed unimaginable distances, passed by uncountable wonders, and finally landed softly on Hubble's mirror, leaving behind a faint but permanent trace. Now we have an even more powerful time machine, the James Webb Space Telescope. Launched in 2021, Webb can see even deeper into the past, not just because it's bigger, though it is, with a mirror over 6 meters wide, but because it sees in infrared. That's key. As the universe expands, light from distant galaxies is stretched like taffy, a process called redshift, shifting it to longer, redder wavelengths. This means that the earliest galaxies now rushing away from us shine mostly in infrared light. Hubble could glimpse some of that light. Webb was built to bathe in it. Already it's showing us galaxies that existed just a few 100 million years after the Big Bang. Some are small, irregular, and chaotic, just as we'd expect. But others are surprisingly mature, like fully grown cities appearing right after the first huts were built. These discoveries are reshaping our understanding of how fast galaxies formed and maybe even rewriting parts of cosmic history. And here's the most poetic part. The farther away a galaxy is, the younger it is in reality, but the older it appears to us because we're seeing it as it was billions of years ago. You might think then that we're always looking into the past, and that's true, but it's also how we learn. We can't rewind the universe, but we don't need to. It has already sent its memories to us one photon at a time, and we are catching them slowly, quietly, with glass and gold and great patience. In a way, this is what science often is, listening to the past, with better and better ears. Of course, all this looking back has its limits. There's a point in time we can't see beyond the cosmic microwave background, the afterglow of the Big Bang we spoke of earlier. It's not that there's nothing before it, but that the universe was opaque before then. Light simply couldn't travel freely. It was trapped, scattered like fog in a dense forest. Only after the universe cooled and atoms formed did light finally break free and begin its long journey to us. That's our cosmic horizon, the edge of visibility. And beyond that lies mystery, possibility, and questions we're still trying to answer. For now, what we do have is extraordinary. Every image from Webb, every frame from Hubble is a photograph of the past, a snapshot of a moment so distant it feels like fiction. But it's not. That light is real. It touched something once, a star, a galaxy, a cloud of gas, and now it touches you. So the next time you stare into the night sky, remember, you're not just looking up, you're looking back, way, way back. The stars are still shining, but many of them are shining from a time when Earth was young, when there were no eyes to see, no names to give them. And yet, their light persisted, crossing space and time to find you here now. The universe doesn't just tell stories, it remembers them. We've traveled far from the first whispers of matter to the sprawling spirals and glowing cores of galaxies. We've watched the universe light up, organize, and evolve. And now, as we drift into the present, we find that the universe is far from finished. Galaxies are still forming, still merging, still reaching toward one another across the cosmic void. Because galaxies, like people, tend not to live alone. Instead, they gather. They form groups, clusters, and even superclusters, massive structures so vast they defy simple imagination. Our own Milky Way is part of one such gathering, the local group. It's a relatively quiet corner of the cosmos, made up of more than 50 galaxies, most of them small and faint dwarf galaxies orbiting the larger ones like cosmic satellites. The local group's two largest members are, of course, US and our neighbor, the Andromeda Galaxy. We're the twin giants of this little galactic suburb, slowly spiraling toward each other. We've already spoken about our future merger, but for now, the two galaxies maintain a respectful distance, close enough to notice each other, far enough not to bump elbows just yet. Surrounding us are a host of smaller companions. Some, like the large and small Magellanic Clouds, are easily visible from the southern hemisphere and are themselves in the process of being drawn into our spiral arms. Others, like the Draco Dwarf or the Ursa Minor Dwarf, are more elusive, faint collections of stars, barely hanging on to their identities as they orbit through our galaxy's dark matter halo. Groups like ours are common, but they're just the beginning. Zoom out, and you find galaxy clusters, collections of hundreds or even thousands of galaxies, bound together by gravity. The Virgo cluster, for example, sits just beyond our local group, and it's filled with spirals, ellipticals, and every shape in between. Here, galaxies aren't politely distant. They crowd together, interact, and often collide. In these environments, you can almost feel the tension, gravitational tugs of war happening across millions of light years. These clusters are embedded in even grander formations, superclusters. The Laniakea supercluster. Our cosmic address, in the largest sense, stretches over 500 million light-years across and contains about 100,000 galaxies. That's right, 100,000 galaxies each, with billions of stars all drifting together through the cosmos. Following the flow of gravity through a web we're only beginning to map, and even that is just a thread in the larger cosmic web, the vast structure that forms the skeleton of the universe. Galaxies are not sprinkled randomly through space. They form patterns, filaments, sheets, and nodes like a vast foam stretched across a dark sea. These structures seeded in the earliest moments after the Big Bang have been shaped over billions of years by the subtle nudging of dark matter and the persistent pull of gravity. In between these filaments lie voids, immense empty regions where few galaxies exist. Some are tens of millions of light-years wide, dark and silent, with only the occasional lonely galaxy drifting through like a ship at sea. It's in this contrast, between crowded clusters and vast voids, that the structure of the modern universe reveals itself. But not everything is growing. Not everything is rushing forward. There are signs that the universe's grand dance may be slowing not in motion, but in creativity. Many galaxies, especially the big mature ellipticals, are no longer forming stars. They've used up or lost the gas needed for stellar birth. We call them red and dead, not because they're lifeless, but because their aging stars glow a soft reddish light and no new stars are replacing them. Even our own Milky Way is forming fewer stars than it once did. It's not done not by a long shot, but the era of frantic starbirth is behind it. We're in a quieter, more reflective chapter of galactic life, and the universe itself. It's expanding faster and faster, thanks to something we still don't fully understand: dark energy. This mysterious force is pushing galaxies away from each other at accelerating speeds. Over the next few trillion years, it's possible that galaxies not bound to us by gravity will vanish from view entirely. Their light stretched until it can no longer reach us. The universe will grow colder, quieter, and more isolated. But don't worry, we've got time, a lot of time. For now, galaxies continue to interact, evolve, and surprise us. With telescopes like Hubble James Webb, and those still to come, we're peering deeper into space and further back in time than ever before. We're catching the echoes of galactic birth, the ripples of collisions, the faint glimmer of newborn stars and galaxies so far away, their light left before Earth had oceans. Every night, sky is filled with those echoes. Every glowing dot is a story. Some are just beginning. Others ended long ago, but all of them are part of this vast, beautiful architecture. Galaxies are no longer just mysteries. They are companions. Teachers' reminders that even in a universe so large we cannot hold it in our minds, we belong to it and it belongs to us. The academic debate surrounding these large-scale structures is an incredibly active and vibrant one. For instance, the exact nature of the voids and how they formed is still a subject of intense research. Some theories suggest they are not truly empty, but are simply areas where the expansion of the universe has dominated over gravity's pull since the earliest moments. Other theories propose that the voids themselves may hold clues to the nature of dark energy, as their growth is driven by this mysterious repulsive force. The intricate pattern of the cosmic web with its dense filaments and empty voids is a powerful piece of evidence that the universe we see today is a direct result of the initial conditions laid down in the Big Bang. It is not a random collection of objects, but a highly structured, organized system. Another fascinating and still debated topic is how the first supermassive black holes formed at the centers of these early galaxies. We see them in very young galaxies, so they must have formed and grown incredibly quickly. Was their growth fueled by the collapse of giant gas clouds? Or did they form from the collapse of the first massive stars? This is a question that requires us to look even deeper into the past, to the first few 100 million years after the Big Bang, a time when the universe was still shrouded in a cosmic mist. The James Webb Space Telescope is giving us our first real glimpses into this era, and the data it is providing is already challenging some of our long-held assumptions. We are, in a sense, rewriting the cosmic history books in real time. The concept of galactic cannibalism, the process by which large galaxies grow by consuming smaller ones, is a powerful illustration of the dynamic nature of the universe. Our own Milky Way is not a finished product. It is a work in progress. It is still growing, still consuming, and still evolving. This is a point that is often lost in the serene, beautiful images of galaxies that we see. The universe is not a static painting. It is a living, breathing, and ever-changing sculpture with galaxies constantly colliding, merging, and reshaping themselves. It is a reminder that even the largest, most seemingly permanent structures in the universe are a part of a much larger, much more dynamic story. And as we contemplate our place within this vast, dynamic universe, we can find a sense of peace in the knowledge that we are a part of it. Every atom in our body, every molecule was forged in the heart of a star that lived and died long ago. We are quite literally made of stardust. We are a part of the Milky Way, a tiny breathing fragment of galactic history. The galaxy is not just out there. You carry it within you. You are a part of this story, and the story is still being written. The universe is not just something to be observed. It is something to be experienced. And in this experience, we can find a sense of wonder, a sense of calm, and a sense of connection to everything that has ever been and everything that will ever be. So as you drift deeper into sleep, let these thoughts settle into your mind. The universe is a vast, beautiful, and peaceful place. You are a part of it, and it is a part of you.